Perfect. Hey, welcome everyone. We're just going to share our screens and then we will get started with our intro to the CISPA European Hackathon Championship Local Hub for Vienna. Okay. I hope that everybody can see our screen. Otherwise, please just feel free to unmute yourself and speak up or drop us a message in the chat. Also, the meeting should be configured such that you will be having the possibility to use a Q&A section. This allows us to answer your questions also anonymously, but I think the easiest part is always if you just drop a question in the chat or if you briefly unmute yourself anytime during the talk to ask your question. So with that, I think we can get started. And I'm very happy to welcome you. Today, it's my big pleasure to introduce our hack. But before we introduce our hackathon, let's first of all introduce us, like Adam and Franziska, whom we're here today. And Adam would get started.
Okay, so hello everyone. Thank you for joining our session. So a little bit about me. So actually, I am a researcher who travels the world to do research in the AI domain, at the cutting edge of AI. And I really lived in many different countries, including I think 7 in total. I worked at Google, Microsoft, investment banks in London, so basically you name it. And currently, I'm faculty member at CISPA, where I co-lead a SprintML group with Franziska.
And I'm Franziska. I also lived in a total of 7 countries actually, and I went to many places to do research. And before I became a faculty at CISPA, together with Adam, we were at the Vector Institute at the University of Toronto, where we worked on cutting edge topics of machine learning. And now we bring that together in a wide portfolio of topics on machine learning and trustworthiness. And to show you the institute where the two of us are working, this is CISPA. And we pointed to CISPA on the map here. We are located in Saarbrücken as a research center on security and machine learning. And what you can already see, the location is extremely convenient because we're really in the heart of Europe, less than 2 hours away from Paris or Frankfurt. And CISPA overall has a very international community of researchers and administrative staff and science support from more than 50 countries. And we're a total of 600 plus people, out of which 40 faculty who do very interesting research on all kinds of topic of machine learning and trustworthiness. And so any topic that is in the area of trustworthiness, privacy, security, machine learning, you name it, we work on. And we do not only work on it, but we're extremely successful on it. So if you look at the CS ranking, which is the standard platform to assess the success of research output for institutions, you will find CISPA in the category of cybersecurity to be the #1 in the whole world, even before leading US institutions. So we're extremely proud that we make this kind of research possible. And we'd also like to show you some faces behind that research from Adam's and my labs. So Adam and I, we co-lead the SprintML group, and our group focuses on secure, private, robust, interpretable, and trustworthy machine learning overall. We are a group of roughly 20 members, PhD students, postdocs, research interns, you name it, and we are in total from 8 different nations. If you want to find out more about our team, you can visit us at sprintml.com. And it's also that team who actually drives the technical challenges of the hackathon. So the challenges that you're going to be working on are based on our team's research. So when we meet in Vienna on December 13th and 14th for the hackathon, there are like quite a few things that you should like be informed of, and that's what the session today is about. So we are first going to give you now a small introduction on what to expect from the organizatorial point of view. And then we'll give you some head start because, as I said, the tasks are based on research, and it might be beneficial for you to look into some of the directions a bit before coming to the venue such that you will hit the ground running. So, about the hackathon in Vienna, it's actually part of a bigger initiative. So, we are running the CISPA European Hackathon Championship for cybersecurity and machine learning. And those teams who win the local hubs, out of which we have multiple across Europe, the three teams that win will get a travel stipend to visit us at CISPA next summer and compete in the grand final. And in the grand final, there are cash prizes for the different teams. So the first team will get a 4,000 euro prize, the second one 2,000, the third one 1,200, and all runner-ups a prize money of 400 euros in addition to their travel stipend. So when you're competing in Vienna, you're not only competing against each other, but you're getting ready to compete against the people from Paris, from Warsaw, from Stockholm, from Barcelona, and from Germany. So get ready. And how the hackathon is organized is in a fashion where we go over the whole weekend. It's basically a 24-hour plus event. And we'll start off with a participant registration on Saturday. So this is the time when you arrive, you get your badges, you settle, you and your teammates get comfortable and take some snacks. And then Adam and I are going to hold the opening plenary where we will provide you with all additional information. And this also includes, most importantly, the concrete tasks that you'll be working on. So that's super important not to miss. Then the hackathon begins. So at 12:30, like we're getting ready, setting up the GPUs, and off you go basically on the tasks. And afterwards, at 5 p.m., the dinner is delivered. And then basically you have the whole night to hack through all the tasks and to get solutions. And then, like, once everybody gets tired towards the morning, we'll be lucky to have breakfast and coffee delivered. And then you have another sprint until 12:30. The hackathon ends when lunch is delivered. And the lunch break also for some teams will be quite exciting because we'll be having the six best teams according to the final scores present their solutions to everyone. So of course, after all this time working on a task, people will be so curious how the best teams solve their tasks. And the presentations will also be part of your evaluation for the final ranking. So the jury will then meet after the presentations and like determine the final ranking among all those teams. And at 3 p.m., we have the award ceremony and the announcement of the winners for this local hub. And then afterwards, it's time to chat to our talent acquisition. It's time to like take some last pictures, and then it's farewell basically. And if you do not want to miss any information during the hackathon, please join our Discord channel. So now before, but also during the hackathon, basically every information is passed through this Discord channel. This comes from like food delivery to how to solve your technical challenges to like questions that arise to the tasks. Everything happens on this Discord, so please make sure that you will be there. Then the last part here is that during the hackathon, already to just mentally prepare you, we'll be having a leaderboard where we show the ranking of all teams. So you will be able to follow like live how well your solutions are doing against solutions of each other. And then you can already see in which task you basically have to invest more and in which task you're already doing very well. And talking about the tasks, let me just get started with a brief introduction, like what is the circle of where the research that we'll be working on is like roughly located.
Okay, thank you, Franziska. So after this intro, we'll get a bit more into the aspects of like what tasks we will be working on. We'll start from general introduction to what kind of topics we target, and then we'll go, I think, slowly but steadily more into details about tasks that you would have to work on during the hackathon. So first is the general intro to so-called Gen AI. So how currently the ML models generate different outputs, images, text, music, and so on and so forth. So currently, probably as most of you know, GPT models from OpenAI, they are capable of generating high-quality text with super high fluency. Now, apart from just the text, models can also actually provide you even proofs for difficult theorems. And then models for Stability AI can follow exactly your prompt and generate photorealistic images. Finally, also other models for music generation, such as from the Suno, they can actually target the given music pieces to, for example, your mood. So all of this actually changes how we really read, how we listen to, and also what we see. Now, how come these models are so powerful? So actually, these models are underpinned by humongous amount of data that is used to train the models. So they are trained on, for example, news articles, different kinds of books, also pieces of art like paintings, as well as music pieces. Now, what is really the problem here is that recently with our students, actually, we showed that models actually can be trained this amount of data that is humongous, at the same time can memorize specific samples. So we showed that we provided the model as training samples, some original inputs, like pieces of this art, of this painting. Actually, model can recreate exactly these input training samples. What's more, it was even shown that some of these models can even memorize the whole books and then generate them word by word, so exactly in the way these books were written. Now, this is really now concerning because this data that goes into the models for training is also copyrighted, meaning that somebody had this creative piece of art and they wanted other people to consume that, but they didn't have in mind, this artist, that these actually pieces of art would finally be used to train the large models. So probably some of you heard about this famous ongoing lawsuit, such as OpenAI versus the New York Times. And why it is a problem is because actually these models form so-called data loops. So on one hand, even now they generate this amazingly high-quality text, pictures, music, and then actually these pieces of generated data are put on the internet. Then model providers actually then scrape them and train on the same data that was actually generated. And this forms the data loop that actually we want to break, since this forms um, of data loops causes model degradation in terms of performance. Now, this also is important that currently EU wants to really prevent the harm of generative AI. And for example, the EU AI Act demands that the providers of these ML models that generate high quality content, they have to actually report what data is used to train the models, as well as what data actually is generated. And then this actually is something that also drives one of the tasks for our hackathon. So how we can really solve these key challenges in current Gen AI? So what we really want is to find out what data actually is used to train a given model. Also, we want to answer the question, what data is memorized by the models? And finally, actually to detect what data actually these models generate. And now Franziska will tell you more about one of the types of generative models, being large language models.
Yeah, thank you, Adam. And I think I'm not telling you anything new when I talk about large language models because probably all of you are already using them on a day-to-day basis. But I just want to give you a bit of background to recap and maybe get prepared for like to look up again, which is a question on how do these models actually generate their data? And this paradigm that underlies the generation is the next token prediction paradigm. So basically, if you have a model like that, and the model has already output like the text G8N, and then it looks at all the tokens that it could potentially output, and based on the highest probability, basically, chooses the final word, which is apple. And then if we wanted to continue the sentence, and that's where the name autoregressive comes from, is that we would take all the tokens we have generated so far, append them to the input, and then like generate the token by token, always like basically based on the previous outputs. And having language models generate this way has two enormous advantages. The first one being that those models adhere to so-called scaling laws, which means that this model's performance scales extremely well as we increase model size, data, and compute. So with all of that, we can get much better. Mm, and I see the question from Tanya, which is whether the slides are going to be made available afterwards. Yes, absolutely. They will be shared on the Discord channel afterwards for you to download. So you will have everything available. The next good part about language models is that they have a very good zero-shot generalization. So the models perform well even when like they're not trained for a particular task. So they can out of the box basically do anything like supervise like classification tasks without being to like needing to be further fine-tuned. And now with all these powers comes of course this question of trustworthiness. And trustworthiness, given that these models are built on data and generate data, depends a lot on the data. And we see these data loops here. And the problems that arise mainly with the data are first of all on the inputs, that they can be copyrighted data, that they can be harmful data, or they can be even wrong data, like factually incorrect. The problem now, and this is what Adam showed with the data loops, is that this can also cause the output to contain the same copyrighted data, harmful examples, and wrong facts. And this is something that we want to look into. And let's first look into this question of which were actually a model's inputs. And therefore, our team co-developed a method for large language models, which is called dataset inference. And dataset inference asks the question, was my model trained on this particular set of data? And the intuition is that the training data leaves a signature into the model, which we can later on detect from the model's predictions. Some of you might already be familiar with something that sounds kind of similar, which is so-called membership inference attacks. And membership inference attacks ask the question for a single sample. So they ask, I have the sample here, can be like a document, a sentence, or a paragraph. And they ask, was this model trained on this data point? And this inference can then be performed with multiple membership inference attacks. And for language models, we have various of such attacks developed. And those attacks usually create some score. So this can be on the like token likelihood, that can be on the model loss of this token. And like there are various signals that can be leveraged. And then afterwards you have all these scores for different data points. And then based on the scores, you can just threshold and say everything that has a value lower than a certain threshold will be considered a non-member. And everything that is higher than a certain threshold will be considered a member. So that sounds so far so good, but the problem is that work like that Adam led to the finding that membership inference actually fails to get confidentially identified training data in such large language models. And the problem here is that every single data point overall just leaves such a negligible effect on the model that you cannot confidently measure it. And there is where dataset inference comes into place. So dataset inference builds on this kind of idea of membership inference, but instead of asking the question for a single data point, like was the data point or not in training, it asks for a whole suspect set. So it takes a suspect set that can be, for example, New York Times gives a set of articles that were published online, and then they provide another set, which is a held out set, which was not published online. And both of that is inferred through the model, and then not one, but many, many mirrors are applied to that. And we take all the scores, and then we do some hypothesis testing to find out whether the data is actually different. So whether the model behaves differently on the suspect data than on the held out data. And you can imagine that, like, what's the intuition here is that if the model has been trained on the suspect data, but not trained on the held out data, the model should behave differently on these two sets. But if the model was also not trained on the suspect data, then both data, suspect and held out data, is data that the model has not ever seen. So it should behave like roughly the same. And this can be expressed in this hypothesis testing, where the null hypothesis formulates that the data set was not used during training. So the sample should look like from any other unseen data set. And the alternative hypothesis assumes that the dataset was indeed used during training. So that means that the model should react differently to it. And so traditionally, then we can distinguish between those if we have this held out data and the suspect data. And with that, we have a powerful tool at our hands to infer what training data a model has seen. But if we now look at the other side, the output detection can be somehow challenging. And I don't know if you have used it. I've started recently using it whenever I get reports to just get like a feeling, like what does the model think? Like, is the text that I'm looking at AI generated? So I copy the text in such a detector, and then afterwards it gives me highlighting of which text was basically suspected to be generated by AI and which one by humans. Of course, these texts can be inaccurate, mm, but like they give us a good feeling, and overall they rely on different techniques like detecting like the text flow, thinking that like the AI text might often be more like grammatically polished, fluent, somehow a bit generic and formulatic, and can be extremely confidently predicted by the model, even if they are like wrong facts inside. Other than that, like we all like as humans have kind of detected our small indicators. So what I often also look out for when I grade students' reports is kind of like some hints that this might not come from a standard keyboard, for example. Like there are these kind of things like non-ASCII hyphens. Like when you type like this hyphen between words on your keyboard and then it's largely generated, it would just be like one hyphen. Here's a double hyphen. Then you see there these kind of quotation marks. So those are also not the ones that you type when you type on your keyboard, but it's like these ones that looks like two sixes and two nines. So that might be a sign that it's generated. Then there are some certain choices of wording which are like relatively uncommon, and the use of like significantly more of the hyphens in the text. All of that can be some form of indicators, which we can use to distinguish text that was generated by some machine learning model versus text that was generated by a human. And it's kind of similar for images. We all still have this, like at least as long as the models are not perfect, some indicators such that you can see the model is not particularly good in rendering text. This is also a research topic that we have recently worked on in our group. Models, some of them are still not particularly good in generating like details of the human physiology, like the hands or the teeth. And all of that can help us basically to manually identify what like images or text were generated by a model versus like by a human. And what we really need is tools to automatically do that with more confidence. And with that, I hand over to Adam, who will in like present a technique that is at least a path towards more confident identification.
Thank you, Francisca. So up to now, we talk about like how to really identify images or text that are generated by models, but without really changing these generations so that we can better detect if a given text or image were generated. So watermarking, the next topic actually, what it enables us is that even if image is photorealistic, meaning that it looks exactly as if it was in the nature, how can we detect if this image actually was generated by a model or not? So this is actually where watermarking comes into play. So it really is the problem that if we have a given image nowadays from these best models, we don't really have a detector that can identify 100% with confidence 100% that actually this actually is generated or natural. However, if we add some watermark either during generation or post hoc, so post generation, then actually the image is in some way marked, and then at least we have some more tools to identify which image actually was generated. So let me introduce you more into like how currently ML models generate images. So Francisca talked about this paradigm that we predict next token. So this actually is kind of intuitive in the language domain, but how it is done in the vision domain actually is very similar. Currently, in the latest models, which are also very aggressive, we generate these images token by token. Here, actually, what is happening is that we do have so-called scales or resolutions with many tokens per resolution. So imagine that you start from some initial vague idea what the image could be. For example, in this case, it is on this slide this resolution 1, and then you have resolution 2, 3, 4, and 5. This K is the full image. But we generate these resolutions actually one by one. So after resolution, let's say 3, then actually we ask model to generate tokens for the next resolution, resolution 4. So we update this image step by step, going from vague idea, then progressing to all details of a given image. So let me tell you more about these current vision autoregressive models. So I will go into a bit more details, but feel free to ask questions if you have any, and I will try to make it a bit more accessible. So how it is really done is that first we train so-called VQVAE, which is a vector quantized vision autoencoder. So idea here actually is that we want to express a given image through tokens. So we get the initial image, we go to the level of tokens, we see how image looks in the form of tokens, and we decode the image to the initial one. So I'll talk a bit in more detail how it is really done. And second part is that we train a transformer model to be able to predict these next tokens. So once we know from the first stage how we can express images in form of tokens, and the second stage actually we also have to be able to generate these new tokens to have new images generated by the models. So regarding this first stage of VQVAE, we start from initial image. We have encoder part of the whole model. So here encode is in form of a convolutional neural network that goes from the pixel space to the latent space. Here the latent space actually is relatively small, 32 by 16 by 16. And actually in this latent space, we can divide this latent space into these tokens. So here is exactly where we have these tokens for images. These are different ways how to create these tokens, but here in this model we have 4096 of these tokens, called also entries in this codebook, this dictionary, and each token actually is expressed as 32 float values, and also this token itself has just index in this codebook. Once we have these tokens, then we can actually from them reconstruct the latent vector of the image and then decode the image again through conv layers into the initial, the output image that we then want to optimize to be as close as possible to the initial image. Now, how do we really train the transformer to be able to predict the next tokens? So here, what is the backbone of the generation is a transformer. Here we start from a start token S, we give it to the transformer, it generates, predicts the first resolution, this R sub 1 hat, and we compare what is this resolution R sub 1 hat to the expected R sub 1. So for the initial image, if we tokenize that, we would have this resolution R sub 1. Then given these two resolutions, R1 and R hat 1, we use standard cross entropy laws to then teach the model how to generate this next resolution. Then we increase to the next resolution, so we have increased number of tokens, and again we have the predicted resolution R hat 2 and expected one R sub 2. We do cross entropy loss and again backprop to the transformer to teach that model how to generate new tokens. Now you see that this is progressive process. We start from this initial idea R1, we go to the final stage of the image R sub k. What is really even more is that state-of-the-art models actually do not predict exactly even the tokens for the images. Actually, they predict on the level of bits. So they actually generate for the given resolution bit by bit the given stage. And now this is actually where our method to watermark these models comes into place. So imagine that we have these bits that we have for a given resolution, and we want to slightly influence the generation of these images to watermark them. So here, what is the case is that, let's say we have in this case, bit 1, and then the question is, what should be the next bit? In our method, we have so-called red and green list. So these are lists of bits, sequences of bits that actually we nudge the model to generate. So for example, in our case, we would like model to generate these bit sequences that come more from the green list than from the red list. So in this case, if the bit from the previous generation was 1, we would like to nudge the model to generate the next bit being also 1 to fulfill this green list. Here we just show a small equation. What is the probability of predicting the bit 1? So actually for the given bit, the model generates probability values for the bit 1 and bit 0, and actually this is probability value for bit 1. We have corresponding probability for bit 0, so we have these two probabilities. And now the question is, how can we nudge the model to generate this bit one, so P1, this probability, and not just bit zero? So we nudge the model through using additional term delta. So this actually is the additional factor that actually we add to the logics of the bit one to push the model generations more towards this bit one in this case. So how do we really use this generation? So how can we then detect the given image actually was watermarked? So we generated this image, we uh, push the model more towards generation of these green lists. And now the question is, if given an image, how can we detect this image is watermarked or not? So we assume that a given image actually is non-watermarked, meaning that when we generate this given image, we have no knowledge about what was the green or red lists. This is our assumption. No watermarking of a given image. Then actually we decompose this image into these bits, and then we actually count how many of these bit sequences come from the green versus red list. If we have kind of equal number of these sequence of bits, so same kind of number of like roughly of the green and red sequences of these bits, then usually it actually means that image was not watermarked. However, if we observe that we have substantially more of the green bit sequences, this actually indicates that this image might have been generated. So with that, I think that we can stop.
Yeah, unless there are any questions of the scientific part so far.
You can also just ask on the discussion meeting chat, and we are more happy to answer any questions. Seems to be that there are no questions as of now. Okay, there are no questions, then we can move on to the part about infrastructure. So probably as most of you know, during the work on ML, we need a lot of compute. And we are so lucky to also get compute infrastructure from Jülich Research Center. It's actually a center in Germany that provides these compute resources for many of the scientific groups. And for this specific event, they were so generous to give to us these 40 compute nodes. Each node actually is with 4 NVIDIA 800 GPUs. Each GPU actually has 40 gigabytes of memory. On this given node for the compute, we have 128 cores, and the whole machine, the whole node, has 512 gigabytes of memory. So these are actually 40 compute nodes where you would just send your main jobs to solve our tasks for the hackathon. Now, once you log into this compute center at Jülich, you will log into one of the so-called login nodes. These are a bit different machines than the compute node that you would primarily use, but if you want to develop your task, work on the initial code, test a few things, naturally you should do it on these login nodes. The login nodes are uh, with a bit different GPUs. These are RTX 800, two of them on a given node. We also have 128 cores and then 1024 gigabytes of memory. However, if you use this compute center, then the login nodes might have many different people who try these different tasks in this case. And the compute nodes, once you get this one of the nodes, then you can fully use that. So this compute node will be just for you, for your specific script. Now, we'll also send to you all the information regarding Jülich, but I would like to just here go through these steps because there are kind of still a few of them, and then it's great if you could do them before the hackathon so that during the hackathon itself, you can just hit the ground running and focus on the tasks. So first of all, you have to register at Jülich. So you just go to this website, gudoor.fz-julich.de, login. Please go there, register. This is the first step. Then once we also are there, we have to accept this multi-factor authentication. It's a very common tool nowadays. Most of the clusters use this tool. For example, in my case, I use Google Authenticator to set this up. I think Francis is using FreeOTP.
Yeah.
So you can choose your favorite tool, and then you have to just enable that. After you get access to some of these resources, you have to also sign the user agreement. So this is a kind of formality, but important. We would like you to work on these tasks. For example, we are kind of always thinking that, work on the tasks, maybe don't mind the Bitcoins. This is this kind of thing that you have to just sign to just confirm that this is the purpose of your usage of this cluster. Now, how can you really access these nodes? How can you really develop your code on the nodes and being able to see these GPUs? So actually, this is done usually through SSH connection. So once you have this access, you have to either create your new SSH key or use your existing one. And then we have this command how to generate the SSH key. And once you have your SSH key, then you just have to manage that in this Julish cluster. There is a field that you have to just upload your SSH key. So let me show you how it works. So here you just have in the from field some IP addresses. What I usually recommend is just copy these IP addresses to these additional public key options to this field. And here in this red rectangle, here you actually have to add your SSH key that you either generated or you just already had. So it's actually, this is where you copy paste your SSH key. Alternatively, you can also just upload your SSH key here using the additional field where you can browse where is your file with the public key. Now, it might take a bit of time. You have to update the database to make sure that actually your SSH key is there before you can really answer, because before you can really access these nodes. Here, what we have actually is that we specify in the command line SSH and then -i, which is the basically the path to your private key, and then your login. So you will also get new login to the Julish. In my case, it was my surname, Jegis4, and then also add this address for the Julish compute. So now, how to really develop the code during the hackathon? What we recommend usually is just writing the code in some form of tool. I think that most of you we know from also previous events use Visual Studio Code, in short, abbreviated as VS Code. So I will just go through that part because I think it's the most popular tool that people use. So here we start from opening Visual Studio Code. We clicked at the left bottom corner, click here. Once you do that, you can just choose which which basically server you SSH to. Here already I have Julish. I'll show you how to set this up. So basically you have to click at this configure SSH hosts, and then you just configure in one of your files, for example, SSH config in my case. Then actually I add these 5 lines. So my host here is Julish, this is your chosen name, the host name, so the address of the Julish compute, my username, different one, I have a couple of accounts, Zdzis is free in this case, then the file that actually you use for the SSH key. And also one of our students actually found that if you're on the Windows machines, you also might add this additional field, max, so then actually if you add that, then it's no problem with your logging to the machines. So now once you have that, you just click on this Julish to SSH to these servers. Once it is opened, you just choose the terminal and then create a new terminal. Then you activate the project. So this might change. This is actually project number from the previous hackathon that we hosted. So we'll inform you what is the new ID for your hackathon. What is the project name? It will be training additional, okay, different number. So you have to activate that, remember, because this actually gives you some variables for your system. For example, one of them is this $ project. So this is a default directory for our hackathon. You create a new basic directory over there, based here on the username. You just make sure that actually you only can access the directory, and then you have your own directory to develop the code. Then we prepared some kind of dummy task where you can just test our API. how to submit your solutions to our tasks. So we have this public GitHub repo hackathon where you can just clone that, and then from here we can start to just uh, trying the API. So how it works is that in this GitHub repo, we have this sample underscore submission.py file. You can just open that. It's just a random kind of submission. And then you can use this actually file to just test the API, how it works. So you have to just replace also your API key, which is here. Here is just none, but we will give you at the beginning of the event your tokens. And then actually here you will replace this none with your token that actually Francisca actually will send to you. And then what we recommend for development, there are different tools people use, but we find that one of the most convenient ones actually is UV. It's a packet manager for Python. You can just copy this command from our slides, and then this is how you can install the UV tool. Then to set this up, it's important to configure this UV. Here are a couple of things that you can add to your .bashrc file. So this is kind of like boilerplate, just copy paste to your .bashrc file. You can just copy that from that. You have just two versions. Here is just how you can, for example, do it with the Vim. And here a couple of additional comments. So you can go through them, you can enable the environments. I think it's very important to do this xbash really, to be able to see these variables that we have. And you can really do easily cd to your project and your directory. Then you can initialize the new environment. Here actually is virtual environment with Python 3.12. We add some packages for the development. For example, we will always need some form of ML tool. For example, here Torch and Torch Vision libraries. Also, Request is our library for the API access. We also have pandas and so on and so forth. You can activate your environment and then actually just execute the sample script from the UV tool. Here actually is how you can really prepare the SBatch script. This is also for accessing these compute nodes. It's kind of also a boilerplate. You can just change a couple of these fields. So this will change a bit, a different number. We'll provide that at the beginning of the hackathon. But most of that actually is, actually this should be dc-gpu, not devel. But we'll inform you exactly, we'll give you this file. I think it's just important for you to know that there is such file that can actually enable you to use these compute nodes with these 800 GPUs. And then actually here you also have just this Python sample underscore submission.py. So this is how you can, for example, like start a new job on the cluster. Here actually it should be your file where you kind of have a lot of compute to be done. Once you have this main.sh script, then you can just start your sbatch main.sh, meaning submitting a batch job to the cluster, and then you just have to wait until your job is finished. And then basically what it means is that you have access to this, in this case, a single node with 800 GPUs, and you can basically start developing the solutions to your tasks. So any questions regarding either scientific part, the ML part, or also compute infrastructure, we are more than happy to answer any questions.
And just as a note, it will be a huge head start if you get familiar with this kind of like UV and like SBatch and Slurm beforehand, because then you can spend your time during the hackathon like focusing on the task, and you will know how to run a job, you will know what to submit it. Otherwise, you'll probably lose the first hour of the hackathon just getting familiar and like getting the first job to run. So it would be extremely good if you focus on like preparing that a bit ahead of time. Also, Abdul is asking the question, how many tasks need to be solved? We always have 3 tasks during the hackathon, and your team is supposed to submit at least a solution to each of those, and the final score will be based on the 3 tasks and their presentation.
So, to maybe just, yeah, I think we also showed that, right? Francisco also talk about that, right?
Yeah, basically, this will be your leaderboard. So you will have the dummy task. This is for you as a warm up. So you will be able to just like try out something to submit there. And then there's task one, task two, and task three. And the overall ranking is just the normalized average over all the three, basically.
Here's second question. Should we set up a virtual machine or just VS Code from a host system? So actually, how it really works is that you don't have to set up any VM. So we operate with the Slurm. Slurm actually is management system for the cluster. So you can have your VS Code locally on your machine, and you just access these hosts from your VS Code that you have locally. But VS Code actually operates on the remote machine. And actually, once you're on the remote machine, you see that actually also in the VS Code. And actually from there you have kind of like directory that is visible from any node. It's kind of one directory. One can kind of think about this as virtual disk. It's a network file system. You can just see that disk from all the compute nodes. And actually over there you just use this S batch to submit your job. And you basically can run your job. Also, maybe I can show that, like once you use VS Code, uh, so I showed this thing, yeah, new terminal. So once you SSH to the Ulyss cluster, you open the terminal, you are actually on the machine which is from Ulyss. So actually it's not even virtual machine, it's just a machine that operates there, and you can just run the code on this login node and then develop the tasks and then submit these as batch jobs to the compute nodes. So okay, okay. I think
There was a
I
question
have
about
more questions.
what
So.
tasks to expect. There is one task which we take as a dummy solution that gives you an idea on like what kind of task to expect. It's a membership inference task, and I've talked about membership inference during the presentation. So like the task is we give you a model, and we give you a file of like 1,000, 10,000, whatever many images, and then we ask you which image was used to train the model, and you're supposed to train a classifier or to find some other solution that will give you some confidence for each of these samples, where we basically then like you can upload between 0, like which means like for sure a non-member, and 1 for sure a member. And then basically we will be running a script in the background to assess what is the true positive rate at the false positive rate at 1%. So basically, you will be graded based on how good you are in like telling apart members from non-members.
Okay, there's also another question from Cheyenne. Are all registrations confirmed? So actually, CISPA will send us with these registrations confirmations soon. According to the email we got for team registration, we are supposed to get a final confirmation from CISPA, which we haven't received yet. This will be sent very soon. Moreover, two of our 4 team members have not got the team registration email yet. Can we just assume we are confirmed for the event so we can book flights, etc.? Very good question. So I think that we'll try to confirm that as soon as possible so that you are sure that you are registered. So I think that in the latest, I think this week, I think we'll try to finalize this thing. We have many people who are interested in this hackathon. This is great, and we'll send these confirmations as soon as possible. If not, please email us, and we will try to make sure that you will get that this week.
The next question is about like the assignment of the compute. And like what we can say here is that we have 40 nodes just for our event. And during the last hackathon that we ran actually until yesterday in Paris, there were no wait times. Like there were wait times from roughly 5 minutes max. You should be good to go.
So also like how we really set up this compute is that uh, you have really a lot of resources, and then thanks to this actually management with Slurm, like once you have this SBatch script and then you just submit your job, then basically it queues these jobs. But in the previous hackathon we had no waiting time. So basically once you submit your job, usually your job is running on the compute node with these 4 800 GPUs. So you have to just, I would say, learn a bit more about maybe Slurm and this SBAT jobs, And I think that this also is useful. Many clusters within Europe, also even we also work in the US and Canada. All of these big clusters actually use such a system, Slurm, for the job management. So this is something that if you will work on ML like large scale or like basically experimentally also heavy jobs, this is the way to go.
And should you bring your own laptops? Yes, you will not be able to work without a laptop. Then the next question is about a team.
Mhm. I don't have a team as of now. What to do? So actually, yeah, this is actually we have this Discord channel. So please join Discord server, and also we have a specific channel for Discord, which is find_team, and then actually you can talk to other participants who would like to attend the hackathon, and you can find a team member or team members. So here we show this find team. So once you join our Discord server, you can just talk to other participants and you can find a team. So maybe why also is the case is that I would say that the tasks are really quite, I think, intensive in terms of like your work, and you have to figure out these solutions. So we recommend that a single team has 4 people, 4 students, because I think that then you can really like distribute a bit of the job. You can exchange on, for example, some tasks, how to solve them. It's not possible that a single person or even a team of 2 people would win the hackathon. In the, for example, previous editions, teams that have really 4 people, they were winning the hackathon because this actually also enables you to really like have this workload divided into your team members.
Also, I just got confirmation from Julian, our administration manager, regarding the confirmations. Like they will be sent out this week. What is extremely important, like our registration is a two-step registration, like the first one and the second one. And in order to be confirmed, we need also the second part to be filled out. So maybe Cheyenne, regarding your message, maybe you can just confirm with your team members that they have also filled out the second part and completed it. Then there should not be any worry. So like both parts are just needed to confirm the application.
Mhm. So Cheyenne says that 2 of the 4 members haven't got the second part email yet.
Then they should just like email us during that week, and then we'll make sure that they get to finish that.
Okay.
So far, like the question is now if there are more like cybersecurity tasks. So all of these tasks are at the intersection of AI and cybersecurity. It's basically like security problems and trustworthy machine learning problems around like AI solution. So there will be no core like capture the flag or so task.
Also, maybe just to maybe give you some more background. So actually, we will also send materials that are actually useful for the hackathon. So potential, for example, papers from conferences that you might, for example, read before the hackathon, so that you can also have the background knowledge to solve this task. So what we really target with this hackathon actually is what is currently the pressing problem of AI, and what also EU emphasizes that we should really work on. And actually, this is why we chose these topics to be the main theme of the European Championship.
All right, we're coming to the end of the session. Are there any last minute questions that we should look into? Otherwise, of course, Discord is open 24/7, so you can just drop your questions there. There might be more people interested in them, so just feel free to reach out over there as well. And if there is no more questions for today, okay. Yes, the solutions are expected to be in Python.
Mhm. So everything that actually we showed here was a Python code. So yeah, in most cases, Python is, I would say, the most popular language for ML development as of now. And our tasks also are provided in Python. So, for example, when you come to the hackathon, we also show you a couple of like scripts how to submit to our API. So, actually, these scripts are also in Python. Um, so, we don't expect that you would be kind of required to develop in any other language. Of course, we have also some Bash scripts. It's also kind of standard.
But
But
we'll be providing most of them.
right,
They're like
right.
everything that you need.
Yes.
It's helpful if you look up what we share here in the slides, then you understand what you will be doing, and this will be helpful if something doesn't work. But other than that, I think you're good to go.
Mhm. Okay,
Awesome.
so we'll try to send this material as soon as
Mhm.
possible. We just have to compile that, the final touches, and we'll send it.
We'll be sharing that over the Discord channel.
Yes.
So looking forward to meeting all of you in Vienna. Have a good day, everyone. Bye.
See you. Bye.